properties of determinants will be very useful in evaluating certain complicated determinants and proving many results. So let us take the properties of determinant one by one. The first property is that the value of a determinant remains unchanged. The value of a determinant remains unchanged if its rows and columns are interchanged. If A is a squared matrix, then the property says that the value of determinant A will be same as the value of determinant A dash, where what does A dash denote? A dash is the transpose of matrix A. And what is transpose of matrix A? A matrix obtained by interchanging the row and column. So that's what the property says, that given is a determinant, and if we interchange the rows and columns, then the value of the new determinant will be same. So it can easily be verified. Now property 2, please note down, if any two rows or columns are interchanged. If any two rows or columns of a determinant are interchanged, then the sign of the determinant changes. For example, here let say delta is a symbol. Usually we denote by determinant A symbol, or delta is a given determinant. A1, A2, A3, B1, B2, B3 are the elements of second row, and C1, C2, C3 are the elements of third row. Now let us interchange the first row and third row, and we write like this, R1, and you know this double arrow R3 means interchange first row and third row, and let the new determinant so obtained be denoted by symbol delta 1. So what do you get? In the first row, the third row elements will come, that is C1, C2, C3, and the elements of the first row will go to the third row, here A1, A2, A3, and what about the second row? That remains unchanged. So it is easy to evaluate and verify that the value of this determinant delta 1 will be negative times the given determinant delta. So delta 1 is negative delta if delta 1 is obtained by interchanging any two rows or column. If the value of original determinant is, suppose, for example 16, and if you interchange any two rows or columns, then the value of the new determinant will be negative 16. That's what it means. Now the third property. Property 3 states, if any two rows or columns, if any two rows or columns of a determinant are identical, then the value of determinant is 0. Then the value of determinant is 0. For example, let the determinant is given as A1, A2, A3, B1, B2, B3, and the elements of third row also are A1, A2, A3. What do you find here? That R1 and R3 are identical, R1 equal to R3, and we want to prove. The property says, so let us prove that value of determinant in this case will be 0. We may expand and get 0, or we can make use of the second property. See how. What if you interchange R1 and R2? Interchange R1 and R2 and let the new determinant be denoted by delta 1. So in R1 you had R1, R2, A1, A2, A3, take it in the third row. And in the third row you had A1, A2, A3, take it in the first row, keeping the second row B1, B2, B3 as such. What do you find? That by interchanging R1 and R3, because R1 and R3 were already equal, it remains the same as delta. But by using property 2. What is property 2? That if you interchange the rows and column, then this new determinant delta 1 should be equal to negative delta, the sign should change. So that means from 1 and 2, if the row, any two rows or columns are identical, on one side it remains the same, on the other side using the property it should become negative delta. So delta equal to negative delta or 2 delta equal to 0, or the value of the determinant has to be equal to 0. So this is a very important property, that if it is already given or somehow we can make any two rows or columns identical, and then the value will be 0. Though let me tell you here that not necessarily identical, even if the elements of any two rows or columns are respectively proportional, then also it will be 0. What is the reason? That we'll discuss after doing property 4. So let's take property 4. Property 4. Please note down, if each element of a row or column of a determinant is multiplied by a constant k, then the value gets multiplied by k. What do you mean by this? That given is a determinant a1, a2, a3, b1, b2, b3, c1, c2, c3. And if each element, say r1, is being replaced by k times r1, if each element of row 1 is multiplied by r1, then the new determinant, say delta 1, what will be the elements of r1? ka1, ka2, ka3, and the rest 2, b1, b2, b3, and c1, c2, c3 remains unchanged. Then the property says that delta 1 will be k times delta. It can easily be proved. See how? If you expand it with respect to row 1, so you get ka1 times this determinant, then again you get minus ka2 and ka1 times and ka2 times, ka1, ka2, ka3. So k will come throughout common and you will get delta only. So the property is simple. Now let us take few results. Please note, number 1, using this property we can take out a common factor from any one row of a given determinant. What do you mean by this note or this property? Let's take an example. Suppose you are given a determinant 2, 4, 6, 5, 10, 15, and say 7, 21, 40. Then what if because you know in the elements of the row 1 are multiples of 2, then this delta may be written as 2 times. 2 may be taken common. So you divide each element by 2, you get 1, 2, 3, keeping the rest as such. Or if you like, you may take 5 common from second row also. So it will be 2 into 3 times, divide the elements of second row by 5, you get 1, 2, 3. Or in the third as such, or you may take 7 common from the third row also to get 1, 3, 2. So the determinant, the given determinant may be written as, 2, 3, 6, 7, 42 times the determinant 1, 2, 3, 1, 2, 3, and 1, 3, 2. So, using the property, if there is a number common in any one row or column, if required, we can take it common. Now, please make a note here that whereas in case of matrix, if you multiply a matrix by a number k, then each element is to be multiplied. Whereas in determinant, we can multiply to any one row or column. And likewise, taking common, we can take common a particular number only from one row or column in case of determinant, whereas in case of matrix, you can take it common from any one row or column. Now, another note, Just look at this example. Say A1, A2, A3, B1, B2, B3, KA1, KA2, KA3. In property 3, I said if any two rows are identical or column, then the value is 0. Now look at this determinant. Here, K is a common number in all the three elements of row 3, so I can take K common and you get A1, A2, A3, B1, B2, B3 and C1, C2, C1, C2, C3. What do you find here? That R1 is identical with R3, so the value of the determinant should be K into 0, that is 0. What's new this time, I just want to emphasize that not merely any two rows or columns should be identical to make the value of determinant 0, even if they are proportional, then also the value of determinant will be 0. Then further I wanted to tell you another note. See, suppose you have a matrix, let me call it matrix. If given is a matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. Given is a matrix this. What will be matrix KA? The matrix KA will be obtained by multiplying each element by K. That is KA1, KA2, K3 and KB1, KB2, KB3, KC1, KC2, KC3. Now, what will be the value of KA determinant? What is the value of determinant whose matrix is KA? So it will be this very determinant. Now in the determinant, you may take K common. What is the value of determinant KA? You may take K common from the first row to make it A1, A2, A3, only from first row. Then again you may take K common from second row, B1, B2, B3, and also from third row, C1, C2, C3. So you get K cube times determinant. So what is the result? That if you have given is a matrix A of order 3, Aij equal to 3 by 3, then the value of determinant Ka will be K cube times determinant A. This is a very important result which you should notice.